In this lecture, we'll be going over models as testable hypotheses. The readings for this lecture are the first chapter in Popper's The Logic of Scientific Discovery, titled A Survey of Some Fundamental Problems, where he lays out his basic principles of deductive reasoning, and Guest and Martin on logical inference over brains, behavior, and artificial neural networks. If you haven't read these, please pause, read them, and come back. This lecture has four main topics: science versus metaphysics, models as mediators, theory versus hypothesis, and a naturally testable hypothesis. Let's start by distinguishing science from metaphysics. Remember that data science is a science. It shares common goals of understanding with science. And the goal of data science is to develop a clear and vertical understanding of the story behind your data by evaluating it from a theoretically principled perspective. What this means is that you have your data, but you lens your data through a common theory. A theory about the mechanics of the world, how the brain works, psychology, biological function, whatever your major theory is. You're lensing your data through that theory. And that's where data science sits. So it's not just understanding the structure of your data, but it's also seeing how your data can vet more abstract high-level theories. If you remove this lens of theory, then what you have is the field of data mining, which is a perfectly acceptable field. It's just curious about the general patterns and structure of your data, but there are different constraints and principles that you have to use when you're doing data mining compared to when you're doing data science. So we're going to focus on the data scientific route, how you lens your data through a theory. Now, one big question here that needs to be settled up front is the problem of demarcation. And this is what Popper was originally interested in the 1930s, 40s, and 50s. And in particular, Popper was trying to deal with the problem of what distinguishes a scientific theory from a metaphysical theory. In other words, what's an empirical theory, or what's an empirical statement, versus a non-empirical statement, a statement that can't really be tested. And in philosophy, and the philosophy of science, there are two main approaches for the construction of theories and understanding through empirical means. First, there's the process of what's known as modus ponens. This is the process of induction. If you're using analytical philosophy or logic, you'll see this statement as the reflection of induction. And what these series of symbols really boil down to, if you write them out in English, is that if P, then Q. Thus, if P is true, Q is also true. This is a kind of constructive additive process. If there's a relationship such that P is related to Q, then if you know that P is true, you know that Q is also true. A kind of classic example of this inductive reasoning is the statement, there are black swans. Now, in order to prove this statement, you have to find the case where P is true. And this requires an exhaustive search. So you keep seeing white swans, white swans, white swans, white swans, and you can only validate this statement, determine that Q is true and P is true, by finding a black swan. Now, this was the predominant form of logic for science for the first half of the 20th century, and was the main purview and structure for logical empiricism and positivism in philosophy. And Popper's main critique is that this is a problem when you're trying to assess scientific theories and statements. If you have a theory written down as a statement or a sentence that you need to prove, if you're using induction, you have to constantly do this exhaustive search in order to prove these more fringe or tail statements, things that are very unlikely but still possible. Popper's argument is that instead, we should take a look at modus tollens instead and perform deductive reasoning. In logic, we would write this statement here, which is, not necessarily intuitive if you don't know how to work with logical symbols, so it really translates to this statement here. If P, then Q. Thus, if P is false, Q is also false. An example of this, classically, is that all swans are white. Now, to disprove this statement, you just need one counterexample. You just need to find one non-white swan, and you can reject this statement. Whereas induction is assembling truths by validation, deduction is assembling truths by falsification. And the idea with modus tollens is that you can't necessarily prove anything, but you can easily disprove things. And thanks to Popper's logic, as well as other philosophers of science in the mid to later half of the 20th century, deductive reasoning has become the bedrock principle of the scientific process. Now let's spend a little bit of time thinking about why inductive reasoning might not make sense as an approach to scientific reasoning. Let's take the somewhat absurd statement or hypothesis that pirates prevent global warming. If pirates are related to global warming, we should see an association between the two. And indeed, if you look at the historical literature, as the number of pirates in the world decreases, the average global temperature increases. Now, this is silly. There's no mechanistic hypothesis to explain why the density of pirate population should relate to global warming, and I think we can all agree this is a somewhat absurd mechanistic hypothesis, but this shows where inductive reasoning can go afoul. Because positive evidence is used as a confirmation of the hypothesis. So the fact that we see this positive correlation this negative correlation in this case, between pirate population and global warming can be used to validate this somewhat absurd hypothesis. And with inductive reasoning, ambiguous evidence is just considered inconclusive, which is true for deductive reasoning. But also negative evidence is still used as evidence of the existence of the relationship. So, had this correlation been reversed, it would still be used to infer a relationship between pirate population and global warming, which, as we pointed out, is somewhat absurd. So, this is the core of Popper's argument against using inductive reasoning for building and developing scientific theories. All you need, you can find these correlations all you want, but all you need for deductive reasoning is to reject absurd theories, not confirm through associative positive evidence. Okay, so what would it take to build a deductive-based theoretical system? Well, according to Popper, one is a system must be synthetic or asynthetic, non-contradictory representation of a possible world. So your hypotheses and your theories are, by definition, synthetic. They're created in our heads and in our collective processes as a scientific community. But it must represent a possible world. It must represent the world of experience. In other words, in order to satisfy the criterion of demarcation between science and metaphysics, this statement or series of statements that represent your theory must be empirically testable. They must represent things that can be measured and physically observed. Also, it must be distinguishable from other representations of experience. So, the only empirical statements are those that can be proven wrong. And this is the core of Popper's model, and it was also other philosophers like Hempel built on this idea that you build models of the world, theories of the world, that can compete against each other. And so you have multiple models, multiple hypotheses that can be distinguished, i.e. proven against other theories. And this allows for theories or empirical statements to be disproven, to be falsified, presenting the core argument for demarcation between scientific and non-scientific or metaphysical theories. For a scientific theory to be true, you must build hypotheses among a world of possible hypotheses that are separable, that can be distinguished from each other, empirically measured, so that they can actually be vetted against each other. You can see how does the evidence support one hypothesis or the other. Now, Popper, in a later chapter of his book, which is a great read, every scientist needs to read his book at least once, specifies the degrees of falsifiability. So falsifiability isn't just a binary state. You don't have a sentence that is falsifiable or not, but there are degrees of falsifiability. So according to Popper, a statement X is said to be falsifiable in a higher degree or better testable than a statement Y if and only if the class of potential falsifiers of X includes the class of potential falsifiers of Y's as a proper subclass, which means that if you have two statements and one contains the symbols or logic or reasoning of the other, then that bigger theory is actually a more falsifiable or a better testable theory. Popper also said that if the classes of potential falsifiers of the two statements, X and Y, are identical, then they have the same degree of falsifiability. The falsifiability of X equals the falsifiability of Y, then they have similar degrees of falsifiability. And finally, if neither of the classes of potential falsifiers of the two statements includes the other as a proper subclass, then the two statements have non-comparable degrees of falsifiability. They're independent of each other. So if you have this class of models and statements and hypotheses that can be tested, some are more testable than others. If two of them are not distinguishable, if they're completely independent statements, then they're not really comparable in their degrees of falsifiability. And for Popper, and most modern science, the more falsifiable a statement, the greater its empirical content. All of our hypotheses and theories, according to Popperian logic, need to be falsifiable, and the more falsifiable a statement is, whether it's a theory or a hypothesis, the greater its empirical content. So this is our goal as science. Generate hypotheses or theories, and I'm going to distinguish the two in a minute, that are as falsifiable as possible. My goal by the end of this lecture is to show you that being able to define hypotheses as statistical models or data models allows for perfectly testable hypotheses and automatically frames your hypothesis in a falsifiable manner consistent with Popperian logic. So let's dig deeper into this relationship between models, theory, and data, because this is going to be a central concept for you to understand in order to see why statistical and data scientific models are important for scientific discovery. There's a large literature in the philosophy of science on the role of models in science as a process. And you can think about this as being a continuum of degree of abstraction. So on the left-hand side here, you've got high abstraction, or very abstract, almost intangible statements. Most of our theories sit here, and the Van Ree and Baggio reading from the previous lecture goes over this idea. At the most empirical, least abstract level, you have your data, your physical observations that you're trying to use in order to understand the world. Now, where do our models sit? Models in science sit as a mediator between theory and data. Essentially, models, when we formalize them, determine how we can test our theory using data. They act as a bridge. And in the new Guest and Martin reading, we get a glimpse as to the delicacy of this relationship depending on your inferential logic. So the Guest and Martin reading for today's lecture focuses on how these models are used in the inference process itself. And they go back to this distinction between modus ponens and modus tollens. Now, as Guest and Martin point out, in modern cognitive computational neuroscience, which I'm also going to argue generally extends to neuroscience and psychological research, you generally have this typical framing of statements in papers. So for example, if I have a model like a neural network that predicts empirical data like neural readout data, behavior, etc., then the assumption is that it reflects that underlying system. So if I have a deep neural network of visual processing that does something that looks like the way humans or other animals do visual processing, then the inference commonly used in the scientific literature is that it is a reflection of that underlying system, the human visual system. That's a modus ponens statement. When you see this logic in papers, it's using inductive reasoning to assume that because the model works in the same way as human data or neural data, it therefore reflects that system. As we just went over, there's a huge fallacy or problem with using inductive inference when trying to evaluate hypotheses and theories. The modus ponens, or the deductive method of this statement, would be that if this neural network model predicts neural readout, brain activity, behavior, etc., then if it's not true, it does not predict. So this is just the modus ponens version of the statement above. So if we have a model that says that there should be some characteristic behavior that we should observe, and we don't observe it, therefore, the model is not reflective of the current system. It is not a useful tool for understanding the brain. Now, Guest and Martin point out that there's a huge problem here in how the inference is being used. What both of these statements show is affirmation of the consequent, and in particular modus ponens with inappropriate causality causes an inappropriate reference to understanding how models can be used to understand the system being described. Modus ponens with inappropriate causality states that if the model correlates with human behavioral and or neuroimaging data, then the model does what humans do. If P, then Q. If P is true, then Q is true. And all this does is self-validate the system trying to be described. It inverts the causal direction. The sense of Q is not contained in the sense of P, but vice versa. So it inverts the causal logic. And what it ends up doing is justifying the explanation of the thing to be explained. And as a result, the logic says that all correlations are valid causal mechanisms. So essentially what you get with using this inappropriate causal reasoning, whether you're using modus ponens or modus tollens, although it's worse with modus ponens, is this self-referential loop. And essentially both of these lines of reasoning for thinking about models as being mediators between how you think the system works and what the system actually does is wrong. So if we go back to this readout here from the Guest and Martin paper, or the figure from the Guest and Martin paper, this is inappropriate causal reasoning. If you wanted to make these statements with appropriate causal reasoning, well then the modus ponens version would be, if this neural network is reflective of the neural and cognitive system, then the model should predict the behavior of the system. And the deductive variant of that, which, as Popper argues, is the appropriate way to do scientific inference, would say that if you think this model is reflective of the neural and cognitive system, then if it doesn't predict the behavior, it is not a true model of the system. And this lower right-hand corner framework, appropriate causal reasoning with modus ponens, is the best way to do scientific reasoning, according to Popper and philosophy of science. So let's understand a little bit why. Why is it that appropriate causal reasoning with modus ponens logical reasoning is a problem. And one of the key problems has to do with the issue of multiple realizability. Guest and Martin used the example of a clock. A clock's function is to tell time. And so its functional role, or a functional role of the system, is the high-level description in terms of how inputs are transformed into outputs. This goes back again to the Van Rijn Baggio reading from the prior lecture. So you want to have some description of its relationship, and you can sit in a descriptive level just saying, well, okay, when the arrows are in this particular configuration, then that tells me that the time is X. That is its functional role. How that function is implemented on the other hand, is a little bit more complicated. So I can have the same function, a clock that looks like this, whose underlying mechanics are classic analog systems, cogs and wheels, or it could be digitally determined. Most clocks these days, even if they have an analog interface, are digitally driven. And that's the mechanistic role of the system, the way in which a function is implemented in a physical substrate. You can have models describing the mechanism, and you can have models describing the function. How does the particular input relate to the particular output? Both of these can be considered models of a clock. And I like this because it highlights the fact that in science there's actually multiple types of models. This problem between describing the functional role of the system and its mechanics distinguishes what I'm going to call generative models, which sit closer to the theory side of abstraction. These are mechanistic descriptions of the underlying system that you think generates your behavior. A neural network model, used in cognitive computational neuroscience, is generally a generative model. A spiking neural network model of a particular neural substrate is a generative model. If you use it to make specific predictions, to generate behavior synthetically, it is a generative model. And a generative model is a slightly less abstract version of your high-level theory. And below that, towards the more specific, less abstract direction of your data, you have your statistical models, which describe function. Statistical models really just say, what are the associative relationships that I see in my data? And you can use your generative model to specify the structure of your statistical models that you use to evaluate your data. So we have now this continuum from high-level theory, which in often cases is very abstract and untestable from a Popperian perspective, to strictly empirical data through these two different types of models. These generative models, which we use to hypothesize about the mechanistic role of the system, and the statistical models, which we use to describe the data. Now, for this class, which is on data science, we're going to focus on these statistical models. These are the type of models that we're interested in for using data to evaluate our theories. And this leads us to having to make a distinction between a theory and a hypothesis. And this is where I think a lot of people get confused, and a lot of text has been written in the philosophy of science trying to distinguish. I'm going to make a very specific case for the distinction between a theory and a hypothesis and how it's relevant to the role of data science in scientific inquiry. And to do this, I need to refine some of my terms. So you have this nested set of concepts, high-level concepts. At the very broadest level, you have your theoretical construct. It's your high-level description of a process or a capacity. An example of a theoretical construct would be working memory. I can't hold a working memory. I can't touch a working memory. I can't see a working memory. But I have this idea that there is this thing called working memory. Now, if you reduce the scope of this concept of working memory to something that is more testable, that becomes its operational definition. This is a reformulation of the theory in terms of a process that can be tested. So instead of defining working memory, I might say digit span, the number of items that we can recall after a short delay. That's something that's measurable. It fits into the broader construct of working memory. So it's a subset or a subclass of statements that are consistent with your high-level theory, but they're testable. They're now that subclass of statements that are falsifiable according to Popperian logic. Within that class of statements that fit within your operational definition, you can generate a hypothesis. A hypothesis is a testable statement about the operational definition as a set of relations. So for example, humans have an upper limit to the number of items they can recall after a 1-minute delay. That is a very specific, very testable hypothesis because it's falsifiable. I can test people in this working memory task and measure the number of items that they can recall and see if this is true. Now, hypotheses themselves are often conflated with predictions. And I'm going to make a key distinction here because the hypothesis itself is evaluated in different contexts. So if we go back for a minute, you might have one context. So for example, the digit span task. That's a very specific neuropsychological task meant to assess a very specific form of working memory. It's an environment that the hypothesis is evaluated in. Now remember, my hypothesis sounds very specific, but if you go back and read the statement, humans have an upper limit to the number of items they can recall after a 1-minute delay, there's not a specificity as to the types of items or what the restrictions are, right? And the digit span task is one task that can be used to evaluate your hypothesis. And within the context and the hypothesis themselves, you get specific predictions. So a prediction is a specific formulation of the hypothesis in a specific context. So for example, recall errors will increase as digit span increases. This is a very specific hypothesis, very specific prediction of a hypothesis in a narrow context. So we go from these very broad statements that include both testable and untestable ideas, working memory, to more refined subset of statements that are empirically testable, according to Popperian logic, the operational definitions, to a narrower test of empirical statements, your hypotheses, that are evaluated in contexts that make very specific predictions. Now I want to dig in a little bit on this idea that your predictions are context-dependent manifestations of your hypothesis. And I think it helps to literally visualize this. Now imagine that your hypothesis is some abstract form, some shape, which we're showing here by this little orb. You could have one context, say the position of the sun and the position of the wall, that says that viewed or lensed through this specific context, your prediction has a very particular shape, this oval shape projected on the wall. In a different context, let's say the sun higher in the sky and the reflection on the ground, the same hypothesis will make a slightly different prediction, in this case a more circular shape in context 2. It's the same hypothesis, it's just evaluated in these different contexts and it leads to these different predictions. This is the way I like to think about the relationship between predictions and hypotheses. So the goal for us is to develop hypotheses that allow for very specific predictions in very specific contexts. And we use data science tools to evaluate them. Now, what I'm going to argue is that when we can structure our hypotheses as statistical models, we can automatically conform to a Popperian assumption of scientific evaluation and empirical content. Let's take a step back and go back to the Van Rhee and Baggio description of a fundamental form of a theory. Recall that in their paper they said that a theory is a theory of capacities, shown here in C, that's described as a relationship between an input and an output through some functional approximation. Now, if you recall from the introductory lecture for this course, the fundamental form of a statistic follows a very similar structure. You've got your output, you've got your functional relation, and you've got your input. So in both of these cases, that function serves as a specific form of description to evaluate the relationships between your data. And I think that Van Rhee and Baggio's description of a functional form of a theory is isomorphic with the fundamental form of a statistic, meaning that as long as you can frame your hypothesis in a functional form that can be evaluated with a particular statistical model, then you have a falsifiable hypothesis. What I mean here is that the form of a statistical test is a quantitative description of the specific hypothesis being evaluated, regardless of whether or not an actual p-value is calculated. We'll get to that later. But because a statistical test is quantitative in form, it is automatically testable and automatically falsifiable. This is where statistics matter in scientific theory. You have your high-level theory, which has statements that are testable and untestable, but as soon as you want to push your statement of your theory into specific hypotheses that can be evaluated, if you can frame those hypotheses as statistical models that can be fit to observational data, then you have framed your hypothesis in an explicitly falsifiable manner. It allows for a purely testable form of your hypothesis. So you want to think about your hypothesis as being symmetrical with the structure of the statistical model you want to use to evaluate your data. Now there's one missing part here. You can form your hypothesis as a statistical model all day, every day. It doesn't necessarily make it falsifiable. So there's one additional feature we need to think about when framing our hypotheses as statistical models. And that's the idea of the null hypothesis. So statistical models are naturally testable hypotheses, but there are multiple types of hypotheses. And in scientific work, we have to consider first the null hypothesis. The null hypothesis is that hypothesis that needs to be rejected based on your theoretical premise. Often it's just the status quo if your theory is wrong. This is a class of possible hypotheses that have the form, in this case of your statistical model, that need to be rejected. So in most statistical inference tests, when you're calculating things like p-values, what you're doing is you're evaluating against a null space of hypotheses. And that's contrasted with your research hypothesis. This is an alternative to the null that is consistent in form with your theoretical premise. And it can be one of many. And this is part of the problem why we rely on Popperian logic, because we can't necessarily prove very easily enough using standard null hypothesis test statistics whether or not the research hypothesis is uniquely true. But what we can do is disprove the null hypothesis. So that means that identification of a null hypothesis, or space of null hypotheses, to be rejected immediately frames your hypothesis as falsifiable and thus testable. So we have two components. We've got the structure of your statistical model, and we have the null space within that structure that defines your null hypothesis. So let's think about this from example. I want to go from high-level theory to hypothesis to statistical model that fits within the Popperian logic of deductive reasoning. Let's say that we have a high-level theory that hunger impairs working memory. Now, stated in this form, hunger and working memory are not operationalized. They're kind of untestable statements. They sit more in the metaphysical realm. If we want to operationalize this into a series of statements that can be tested, we would say that hunger is defined as the bodily state that occurs when no food is consumed for 4 hours or more. And we could define working memory as the number of items that can be recalled after a short period of time in the DSPN task. Now, if we make these operational definitions of our term, we reduce the space of the statements to those that can be falsifiable, then we can put together our hypotheses now. So the null hypothesis is that digit recall does not change with hours since last meal. And the alternative hypothesis is that digit span or digit recall reduces with time since the last meal. However, this is not the only alternative hypothesis. There's another research hypothesis that says that digit recall increases with time since last meal. So let's think about these two research hypotheses and the null hypothesis in the context of our statistical models. If I wanted to define the full relationship of my hypothesis between my variables, I could use a regression model. So this would be the functional form of my hypothesis space. Y is the digit span recall. X is the time since the last meal. And I have, in this case, two parameters of interest. One that's the primary parameter of interest in this model, beta 1, which reflects how much a change in time should associate with a change in digit span recall. And then your beta naught is just your intercept term. So according to the way we stated our null hypothesis, if the null hypothesis is true, we should see something that looks like this. The line that describes the relationship between time since last meal and digit span should be flat. Our first research hypothesis states that we should see a negative relationship between two. So the slope of that line, the beta 1, should be negative. And so in our hypothesis space here, we would say that the null hypothesis is that beta 1 equals 0. The alternative hypothesis for hypothesis A is that beta 1 should be negative or less than 0. And the contrastive research hypothesis, hypothesis B, is that that slope term beta 1 should be positive. Now we can make conclusions about whether or not hypothesis A or hypothesis B is correct based off of the observed direction we get when we actually empirically run this experiment. However, the pure form Popperian approach states that we're only concerned with rejecting the null hypothesis, that beta 1 equals 0. That reflects the space of hypotheses that are the status quo of no associative relationship between X and Y. And that is the one that we try to falsify. So I hope this makes clear that if we can frame our hypotheses in the form of the statistical models that we intend to use to analyze our data, we automatically frame our hypotheses in a testable manner according to Popperian logic. But in order to do that, we need to have a concept of a null space, a space of hypotheses whereby the status quo or prior assumptions are true that is to be rejected. When you have those two together, every hypothesis statement you put that has that form follows Popperian logic. Okay, so I hope that you've taken away from this lecture that falsifiability is the main demarcation distinguishing science from non-scientific inquiry. If you can frame statements in a falsifiable form, and the more falsifiable they are, the more they're consistent with empirical content, then you have statements that are consistent with science. In addition, I showed how models act as this mediator between these abstract high-level theories and more concrete empirical data. And of the models described, statistical models in particular function as an inherently falsifiable hypothesis generated from your high-level theories. And the statistical models themselves represent a purely falsifiable structure of your hypothesis. And if you can frame your hypotheses as statistical models before you start collecting data, you've automatically made your hypotheses consistent with Popperian scientific logic.